issue is you don't know what x starts with, right? It could start with a b, or it could start with a c, or I suppose x could be the empty string. I'm just going to do derivatives with respect to b to the I. Or you could use c to the I. It doesn't matter. Either way, we'll get basically the same result. And this is the one where I am now imagining that x begins with b to the I. So I imagine that x looks like b to the I y. And then I cancel off that b to the I. So what does the rest of it look like? If x equals b to the I y, then x a to the n x looks like b to the I y a to the n b to the I y, right? If x is b to the I y. And then when I do the derivative, it cancels these b's at the beginning, and what's left is all of this stuff. So this di, which is derivative with respect to b to the I of L, is just going to be y a to the n bi y. And those are all different because, say, when I equals 1, it means there's one b right here after the a's. When I equals 2, there has to be two b's after the a's, and so on. These are different for various I. Sorry, I was a little mixed up on this example. But this is meant to be like a harder one. If you see sort of unknown variables in here, it can be a little trickier to deal with, but not much. Yeah?
What does it look like when you do one of these derivatives on a regular language?
Yeah, if you do it on a regular language, they will not all be different because regular languages have only finitely many derivatives. What does that actually look like? So this is a great question. What if I just tried to do that on something like a to the n, b to the m? So this is actually, that's regular because you could, for example, this is a regular expression, a star, b star, right? So that definitely is regular. What if you tried the same business? You would try, so this is not going to work, but you would try to do derivative with respect to a to the I of L, which is a to the n minus I, b to the m. And then you would say, those are all different for various I. There's got to be, something's not right about that though. Anybody remember? Actually, it's a fact, those are not all different from various I. Can anyone say why? These are actually the same for all I. Anyone say why? They don't look the same, but really they are in truth.
Like every time you increase I, it would just be 1 less A, and it wouldn't. Oh, wait, n can be anything, so the I effectively doesn't like that.
Yeah, n can be anything. So this, like the original one says, some amount of A's followed by some amount of B's. And those two amounts have nothing to do with each other. And what does this say? Well, it also says some amount of A followed by some amount of B's. The fact that you put a minus I here doesn't matter at all, because these two variables are not related to one another, and so I'm not saying anything special. The difference over there is those two exponents, they are related because they both have n's in them. So you're saying the first one is twice as much as the second one, or twice as much minus 1 as the second one. But here, they are just two different numbers which are not related at all. And so these are actually the same. All of these languages, they are still the same as A star, B star. Some amount of A's followed by some amount of B's. All right. Anything else we can talk about on the list, either of the lists? Probably what I wanted to say about the PCP will probably take 15, 20 minutes. So we do have some more time to talk about review type topics. Yeah?
For the RE versus recursive,
yes.
Do we need to just be recursive, it always accepts, or it will always either accept or not accept, and then RE is it can go forever or whatever? Is that all we need to say about it, or do we need to?
I think you should know what you just said.
Okay.
I mean, I might ask you a question that requires you to know that, but I wouldn't expect you to know much more than that. Yeah. know this is a little vague.
So like would it be like proving something is like RE or whatever?
Well, I suppose. So proving, yeah, I probably wouldn't ask it in that way. Like proving that a language is RE is the same as just showing that it is a language accepted by some Turing machine. And so, like if I said something, so a question, you should expect me to ask a question, something like, make a Turing machine for, I don't know, A to the N, B to the N. This is like a very simple matching type Turing machine. Or I could say, it's exactly the same question to say, prove that A to the N, B to the N is RE. Because what that means is there is a Turing machine that accepts this language. So if I wanted to be sneaky about it, I could ask it in this way, although I probably wouldn't, but they are the same as each other. You all right? All right. Yeah.
How is A to the N, B to the N recursively enumerable?
RE means it is the language accepted by some Turing machine.
Okay.
And it is. I mean, as far as like our it's even more than that, but like, remember our like big sort of categories of languages? RE was the largest category. So like A to the N, B to the N is even, here's regular, here's context free. A to the N, B to the N is actually context free. So it's definitely, it's like automatically RE for that reason. It's even more restricted. Maybe you're imagining RE contains something like the language of the halting problem. What's interesting about that is that it's RE, but it's not in any of the lower categories. But even the like more ordinary languages are all in these lower categories, but they're also RE. Yeah. All right. Great. Let's talk about the PCP a little bit. And then we can talk about more of this stuff if you like at the end. This is my last class of the semester, by the way. Any of you seniors, last class ever? Is it? One more for you. All right. Well, I hope it's all worth it. Will has helped us out. You've been a student your whole life. This is it. All right. Okay. Hope it's not a letdown. So my goal for, what I wanted to say, which like I said, we'll probably talk about for, 15 minutes or so. The idea is that PCP is uncomputable. I will refresh your memory about what that means. It means, so the idea of the PCP is you have a certain amount of blocks like this. I'm just making these up, so I have no idea if this one is solvable or not. They can have empty strings on them if you want. And then and I would ask you, is this PCP solvable or not? And the answer involves lining them up in such a way that when you read the string across the top, it equals the string when you read it across the bottom. Now, these ones, as lined up as they are, do not solve the problem, but maybe it is possible. If I go 1, 0, and you have to start with the starting block here. So 1, 0, 1, 0, 1, that could be my first one. And since I just made this up, I don't know if this is possible or not. Anyone have a feeling about it? I think it's probably not possible based on what I did here. The next tile that I use has to begin with a 1 on top because I need to make this string across the top match the string on the bottom. That's not very helpful, I suppose. I could use any of these. I don't think that this is possible. Can I just say probably not possible? You are allowed to reuse any of the tiles as many times as you want. But our goal is to show that the PCP, that no algorithm is capable of solving all examples of this weird little puzzle, all right? And the way in which we do that, so Post showed that any PCP solver, if you could imagine some kind of method to generally solve the PCP, could be adapted to a halting problem solver. And that we already know is impossible. Right? A halting problem solver cannot exist, and so therefore this means that PCP solver also cannot exist. And I want to show you specifically how it's done because I think it's really cute. Let's do a particular example here. So this is not really post-full proof. You can read his paper about it if you really want to. I'm going to just make up a simple Turing machine here. This is a Turing machine which well, we don't really need to talk about everything that it does. It's a simple Turing machine, though. One thing that's slightly weird about this is I have a looped arrow on the accepting state. Now, remember, a Turing machine, as we usually discuss them, once you get to the accepting state, just everything stops and the string is accepted. Although I we'll use Turing machines just for the sake of making this PCP argument a little bit easier to argue. We're going to use Turing machines that accept and clear the tape. All right? Any Turing machine, you could, if you want to, make it so that after it accepts the string, it just blanks out the whole tape. And that's what this does. So once the string is accepted, it does that and it moves to the left throughout the whole tape and turns everything into a blank. All right? So I'm going to call that a Turing machine that accepts and clears the tape. Any ordinary Turing machine, the way that we usually describe it, you can easily modify it so that it clears the tape at the end. So this is not really a special category of Turing machines. All right, and I would like to ask, let me put a state 3 on that one. Is the string A, B accepted? Now, in general, that question is computationally a very hard one. If I just showed you a random Turing machine and asked you, can you tell if this string is accepted or not? That is, in some sense, it's not the same, but it's similar to asking, does the Turing machine halt or not? Which is a hard question computationally to answer. But you can just sort of try and work this out and see what will happen. We can write a derivation, and this might be a nice thing to know how to do for the sake of doing the final exam. A derivation on this machine, we would write it in this way. So we begin in state 1 and write A followed by B. That's the string that we begin with. And then can we write out in steps, what happens here? If you're in state 1, I'm reading this A. It stays as a moves to the right, and goes into state 2. So the next thing will say A to B. That's because the head moved to the right one position and transitioned into state 2. Now in state 2, I see a B. B stays like it is. I stay in state 2, and the head moves to the right one more position. So the next step will say A. Something's wrong with this. A. No, nothing's wrong with that. Sorry. Like that, right? A, B, 2. And now 2 is looking at a blank. I do the BBL line, and this will now say A3B, right? It was in state 2. State 2, seeing a blank, changes to state 3 and moves to the left. So the head moves to the left one and becomes a state 3. So it now says A3B. And then 3 so here I'm in the clear the tape now state. So it will blank this out and then move left. So it'll say now 3A, because it blanks that little b and then moves left. And now it's going to blank the little a and move left, and then it'll be sort of totally done, which it'll just look like 3. All right? And then just for fun, I'm going to do this arrow and then some kind of a, smiley. I don't know. It's accepted, right? That indicates that the string was accepted because I made it to the accepted state and then cleared the whole tape. All right? Check it out. Okay, I hope that this is all sort of non-controversial. This is a fairly simple workout, the what happens on the Turing machine. And I hope everybody remembers how to do this. I'm going to show you how actually you could translate this entire procedure into those blocks with the thing on the top and the thing on the bottom. All right? And this, I think, is a really cool idea. So here's Post's idea. You convert the entire Turing machine into those kinds of blocks with the thing on the top and the thing on the bottom. So we have, first of all, the individual letters, and they make a block that says that, and another block that says that, and there's a special block that says that. Because I want to be trying to use the blocks to reproduce this bunch of transitions, all right? So there are blocks representing each individual letter in the alphabet, plus this kind of turnstile block. There's also blocks representing the moves to the right. And they are like this. If you think about each of the arrows in the original diagram, like the first arrow, sorry to scroll away here, this first arrow, AAR, going from state 1 to state 2, you can think of that as a rule for rewriting. Whenever you see 1 followed by A, that can turn into A followed by 2. Because if you see 1, if you're in state 1 and you see an A, that's the same as moving past that A and then going to state 2. So here, there is a block which represents that fact, that if you start with a 1 and look at an A, that's the same as moving to the right past that A and changing into state 2. And then each of the other arrows, I'm going to make a block out of them. So there was an arrow with a B on state 1. It was looped back to state 1. So that B looping back to state 1 arrow becomes this block. There were 2 other arrows which moved to the right. One was like this, and one was like this. All right. And then there were some moves to the left. The leftward moves are a little bit of a pain to deal with, but I have one that looks like this and one that looks like this. So these 2 leftward moves are the ones, sorry, I meant to have a 3 on the bottom. B2, 3B. This corresponds to being in state 2 and seeing a blank and then moving to the left and changing to state 3, like that. And this, I think I meant for this to be a 3 also. Sorry, that's a typo. This is if you're in state 2 and you read a blank, you move to the left and go into state 3, all right? And then there were also similar ones. If you're in state 2 with a blank on the right and a blank on the left, you can move into state 3 with a blank on the right and on the left. There is similar ones. These all represent moving to the left and blanking a single letter. So here, if you are in state 3 looking at an A, you should blank it and then move to the left. But you have to, unfortunately, this is sort of technicalities. You need 2 different cases depending on what you saw, what you had on the left of the A there. I have a few more versions of those movements, and then we'll get to the good stuff. There's also A, 3B, 3A. There's also B, 3B, 3B, and finally 3B, 3. All right? This one means if you're in state 3 looking at a B with nothing on your left, then you end up in state 3 by itself. All right? And then, finally, there is one to represent the accepting state. And it's that. So this is a special tile which indicates that 3 is an accepting state. Really, I'm giving you a way of translating any Turing machine, any kind of thing from the Turing machine diagram into one of these PCP things. And then we also have a tile which indicates the starting state. And that one looks like this. It has epsilon on the top and then 1 AB arrow on the bottom. This is weird, but this indicates that we are beginning the computation with We're starting in state 1, and we're starting with AB on the tape. All right? Okay, so those are all of the tiles that correspond to the various arrows in the Turing machine. The idea is we have translated the entire Turing machine diagram into these PCP tiles. Now, does this have anything to do with whether or not strings halt or are accepted or whatever? Check it out. It actually does. So it turns out that a string is accepted on the Turing machine if and only if this PCP has a solution. And that means that if you know if you somehow magically are able to solve the PCP, you automatically will be able to solve the question of whether a string is accepted or not on the Turing machine. And that is undecidable, because that is a variation of the halting problem. So look, check it out. This PCP has a solution, because we already know, like I did an example already of this all of this business. 1AB goes all the way to the end. It turns out actually the fact that this is possible on the Turing machine means that there is a solution of this PCP, because they both represent the same thing. I'm going to start with the starting block. It has epsilon on top and then 1AB arrow like that. And I'm going to try to reproduce the original derivation that I did on the Turing machine. Maybe I will just copy it down here so I don't have to scroll all the time. I'm going to try to copy this, but using the blocks. So it says 1AB arrow. The next thing I want to see is A2 on the bottom, because I saw 1AB arrow. I want to see A2 here. What block should I use to do that? Actually, there is a block with A2 on the bottom and 1A on the top. So I'm going to use the block 1A, A2, right? And I will point out, actually, if you read the bottom string and the top string, actually they are matching so far. I have 1A on top and 1A at the beginning on the bottom, all right? What should come next? What block should I use next? My goal is to reproduce this derivation using the blocks. Which block do I have to use next? Sorry, it's impossible for me to keep everything on the screen. You can see them all now. Which one should be next? You can't see the derivation though. Yeah?
Is it the BB?
Yeah. I see B on the bottom, right? The next letter I want to see down here is B, because I'm trying to create this derivation. It says A2B, right? And what do I want to see up top? Well, in order to match where I started, because this string up top has to be the same as this string down at the bottom, I want to see a B also. Yeah, I'm going to use the BB block. All right, what next? Somebody else want to tell me? I'm trying to create this string across the bottom and across the top. Yeah?
The transition.
Yeah, the arrow is what I need to see next. It needs to say A2B, I'm like here now. Next I need to see the arrow. And lucky for me, I also need to see the arrow on top. It's not lucky. This is the beauty of Post's construction. It turns out, we are presently demonstrating that following these blocks is actually the same as following the steps in the Turing machine. So on the bottom, at least, I'm kind of here. On the top, I'm back here. But anyway, what I want to see next is A followed by B and then 2. Now, next on top and bottom, I want to see A. So I'm going to use the A block first. The way I know that is I'm thinking, like in this step, actually, you're not doing anything to the A. So the A should be the same. What is happening is over here I see B2, but over here I see 2B. So there is a block, though, that says 2B, B2. It's kind of like the top and the bottom of the blocks it's like the bottom is kind of the step I'm at here, and the top corresponds to the previous step in the same location. And How do you know those two steps are going to match up appropriately? Well, they will match up appropriately because I'm doing the proper steps that work on the Turing machine. Whether or not a step works on the Turing machine is the same as whether or not it works in the PCPs. All right, so I am, let's just finish this off. I'm right here now, so next I want to see the arrow. All right, now, at least on the bottom derivation, I'm here. I want to see A and also A on top, so I'm going to put the A and the A here. Next, I want to see 3B on the bottom, and on the top, I want to see B2, and hopefully there is such a block. There is, right here, B2 and 3B. So I put B2 here, 3B here, all right? Now, on the bottom string, I'm here. Next, I want to see the arrow again. Let's continue. Maybe I'll move this guy down. Okay, I just put this arrow, at least on the bottom here. Next, I want to see on the bottom 3 and A. And the top, I guess I want to see 3 and B. Is there such a thing for that? Oh, no, I need to see A3B. There is a A3B. Sorry, I scrolled back a lot. A3B and 3A right here. Is that it? No, here, this one. A3B up top, 3A on the bottom. So the next block, A3B, 3A. All right. Now I have 3A on the bottom. Now I see the arrow again. Now I want to see just 3 on the bottom and 3A on the top. And there, again, there is a block that says that, I think. Just 3 on the bottom and 3A on the top. Oh, I left it out. I should have wrote that also right here. This is a left-moving transition from an A that blanks it out. So there's a block, 3A and A. No, 3A and 3. And then finally, I do the very last accepting state block is this, 3 arrow and 3 on the bottom. Sorry, this is another typo. It should be an epsilon there. Now I'm really... I'm letting down the seniors whose last class, this is their last schoolroom experience in their lives. Now I'm done, all right? And all the blocks, they do fit together. And the top ones, if you read the top one across, what you see is exactly this. And if you read the bottom one across, what you see is exactly this, all right? It means if you are capable of answering questions about the Turing machine, all of those questions are equivalent to the same questions asked about the PCP. And that means if you somehow had some kind of way of solving the PCP in all cases, then you would automatically have a way of solving the Turing machine. Does it accept or not in all cases? And that is impossible. All right. Sorry, my somewhat confused blocks here. Any thoughts about that? So this is the language that they use is Post showed the PCP is unsolvable by reducing it to the halting problem. That is, he showed somehow that you could take any Turing machine and encode it inside of this PCP setup. And there are many other things which have since then been shown to be unsolvable, and it's basically always done in a similar way. So I mentioned last time that the solution to all integer polynomials, like solving a general integer polynomial, is also uncomputable. The way that somebody proved that, I believe that wasn't actually proved until like the 1970s, but the way that somebody proved that is by somehow showing that you could start with any Turing machine and convert it in a weird way into a big polynomial, and then show that being able to solve that polynomial is equivalent to being able to solve the halting problem in the Turing machine. This is how these kinds of things are done. All right, and I think I will leave